Right now, it is like, I don't know, 11 a.m. And I'm not gonna lie, I've been playing Adventure Capitalist for like 2 hours this entire morning. So it's time to make a video. Alright, so this video is it's gonna be about average velocity and average acceleration. I'm gonna teach you how to solve for those with some word problems. And we're also gonna cover derivatives and integrals of velocity. So I'm just gonna start the relationship. I'm gonna tell you guys what the velocity relationship is with acceleration, vice versa. But that's gonna be probably a different video when I actually have you interpret that. So first thing we start is the average velocity. So let's use some formula. The average velocity is equal to in your change in actually just displacement. Actually, your change in position, which is displacement, over your change in time. So usually it's just going to be time rather than change in time. And your acceleration is equal to your change in velocity over the change in time. So remember, acceleration is how much your velocity changes over time, and your velocity is how much your position changes over time. Let's do a quick problem related to this. So your average velocity, what's your average velocity if you're at position 5 meters? Let's say you were on some number line and you were at this position 5 meters, and then now you're at 25 meters after 20 seconds. What's your average velocity? So the reason why you use average velocity is because your velocity could have been, I don't know, 20 meters per second for 0.01 seconds. And then it could be 0.01 meters per second for, I don't know, 3 seconds, right? And then the rest balances out. But overall, even if your velocity changes a bunch, you still end up 20 meters ahead after 20 seconds. So average velocity is very helpful because it's good for calculations. It's something that's constant. You don't have to represent it with a function. So average velocity can be very useful to find. So how can you solve this problem? Well, your change in position is, well, I already said it. Your change in position is your final position, 25 meters, minus initial position. And this is equal to 20 meters. So this is your change of position. Now keep in mind, whenever you're using velocity, if you were to go to 0 meters, for example, as your final position, so let's say this was x final, this was x initial, then your displacement would be negative 5 meters. So you would have to keep in mind the negatives and positives here if you were to, since you're using velocity, but we're not worrying about that for now. And your change position is 20 meters, so we just divide that over change of time, which was 20 seconds. So you get 20 meters over 20 seconds is equal to 1 meter per second. And the units make sense. You have the meters over seconds here, and 20 divided by 20. And these meters per second turn to velocity. The units make sense in this case. That's how you know you did your problem right, or your equation is right. Okay, let's do a quick problem with the acceleration. Okay, let's say you went from 10 meters per second to 0 meters per second in 5 seconds. Try to solve for this. So your change in velocity is negative 10 meters per second. So I'm trying to ingrain that in your minds. Negative and positive matter a lot when you're talking about vector valued or vector variables. Variables that can be that are vectors. Acceleration and velocity are vectors, so they have direction. So negative and positive matters. Now, if you saw speed, for example, speed is the scalar form of your velocity, so it's just only positive numbers. But your average acceleration is negative 10 meters per second over 5 seconds. 5 seconds is the change in time. So I bit my cheek when I was sleeping. I wear like a mouth guard and I grind my teeth at night. And dude, this thing is like so annoying. So I have to I'm kind of talking with a lisp right now. So your average acceleration here is just negative 2 meters per second squared. And again, the units make sense. You have meters per second over seconds, and this is equal to meters per second squared, and this is the unit for acceleration, so that's how you know you got this right. On a quick side note, I am teaching you guys calculus-based physics, so I'll cover derivatives. So your velocity is the derivative of position with respect to time, and your acceleration is the derivative of velocity with respect to time. So what does this mean? Well, just treat x. So if you had a graph, for example, you treat x as the y-axis, and you treat t as the, I guess you have to have a negative, or you treat t as the x-axis. So whatever's at the bottom of the fraction in this Leibniz notation of your derivative, t will be, the bottom part of your fraction will be the x-axis of your graph, and the top variable will be the y-axis. And if you were to just graph your change of position over some period of time, your derivative of this would be your instantaneous velocity. So I need to write instantaneous. And again, if your change of velocity with respect to time is acceleration, then you would have some graph where the y-axis was the velocity, and the y-axis was the velocity, and the x-axis is your bottom variable, or time in this case. So this is just a quick cover of derivatives, and you can do the same thing backwards, especially with derivatives. Your integral of acceleration with respect to time is your velocity, and the maybe more specifically your change in velocity, and your integral of velocity with respect to time is equal to change in position. Now for this problem, you're going to be using something slightly different than what I've been covering. You're not going to use change in position, but you're going to be using this variable right here. Your average velocity can be represented by v initial plus v final over 2. That's your little hint here. So if you were to use your change in position over change of time, well, you would have to use kinematics in order to solve for your change of position. More specifically, you would have to use your this formula here. Delta x is equal to v initial times time plus 1/2 acceleration times squared, in order to solve for your delta x in this equation given the information. And your change of time is just 6 seconds here. But I'm assuming if you're learning average acceleration, maybe you haven't covered kinematic equations, so I'll solve this without kinematic equations and just use this simple formula here. So v initial is obvious. It's given. It's 2 meters per second. So this is v initial. And your v final, it's not given. It's not so obvious as v initial, but your v final is 8 meters per second. And let me tell you why. Well, after 6 seconds of constant acceleration of 1 meter per second squared, you have gained, so each second, you gain 1 meter per second in your velocity. So if 6 seconds has passed and each second you gain 1 meter per second, each second you gain 1 meter per second, given by the definition of the acceleration. After 6 seconds, well, your change in velocity is 6 meters per second. If you add your initial velocity onto your change in velocity, you get 8 meters per second. Oh, that's a bad box, which is exactly what your v final is. So I'm going to erase that for some more space. Actually, we don't even need the more space. I'll leave it there. Maybe I'll use it for the thumbnail. But now we have v initial and v final. So instead of using some kinematic equation, you can just use v initial plus v final divided by 2 in order to get your v average. And this divided by 2 is just 10 meters per second. 10 meters per second over 2 is equal to 5 meters per second. So 5 meters per second is our average velocity in this case. Now, this problem has some words in it, but don't be scared. The words just describe uh, the math that you're doing. I remember when I was a kid, word problems were at the absolute bane of my existence because I hated reading so much. But, growing up, physics is literally all just full of word problems when you're doing your exam. So, let's do this one. So, read this first, and I'll explain the logic behind it afterwards. So assuming you've read it, I'm going to describe what's going on here. So we're going to assume this is in a one-dimensional plane or surface, one-dimensional path. So you're just traveling straight to the gym and straight back. And on the path to the gym, I don't know if you yawned there. Yawns are quite contagious. But that was not my intention to make you yawn. I'm just tired. It's in the morning right now. But it's 5 kilometers to the home and to the gym. And let's solve for the average speed first. So this is going to be a little different because average speed doesn't use change in position. It uses distance traveled. So it uses distance over time. For average, let's use S for speed. Average speed. Distance over time. So change in position for velocity would be 0 because you end up in home anyways, right? Technically, every single day, your average velocity is 0 because you just end up on your bed every day, unless you move maybe. But your average speed is different. Your average speed is the total distance you traveled over time. So that's a key thing. Speed is the non-directional version of velocity. So for the speed, well, the total distance you traveled is to the gym and back. So this is 10 kilometers. So distance, let's use D. So distance is equal to 10 kilometers. And now we have to solve for the time it took to get there. Well, we have our speed and we have this distance. So in order to solve for the speed and the distance, in order to solve for the time using speed and distance, you just have to use a little bit of unit conversion work. But if you divide, technically, let's use division. If you divide the distance by the speed, so 60 kilometers per hour, you get the time. So if you divide distance by speed, you get time. And this is 1 over 12 hours, which is technically 5 minutes. So 5 minutes. I'll just write that down up here. And again, on the way back, 5 kilometers over kilometers per hour. So this is on the way back. This is to the gym. So to gym to home. And this is just 1 over 8 hours. So your total time that you spent, so this is 1 plus 12 hours driving, is equal to 1 over 12 plus 1 over 8 hours. And this is equal to 5 over 24 hours. And if you were just type that into the calculator, 5 divided by 24 is like approximately 0.208 hours. Hours? I'll try hour. So you have your time and you have your distance. So you have your distance and you have your time. So you can solve for the average speed now. So the average speed is equal to distance, 10 kilometers. So distance, remember, distance does not change in place. What word did I use? Change in position. Oh my god. Distance does not change in position. Distance is total distance traveled. So you went 5 kilometers to the gym, 5 kilometers back. That's why this is 10 kilometers. And your change in time is calculated by using your speeds back and forth. So your total time is 0.208 hours spent driving. So if you were to divide 10 by 2.08, then you would get 48.08. This is approximately kilometers per hour. And if we use some unit conversion, so you get 48 48.08 kilometers per hour times 300, times 1 hour. 1 hour is equal to 3,600 seconds times 1 kilometer is equal to 1,000 meters. So your final answer, using some unit conversion, would be, so divided by 3. I'm typing this in my calculator, so I'm repeating it. 13.4. I'm running out of space. Hold on. Let's write it down here. 13.4 meters per second as your average speed. Now I've already hinted at your average velocity and how to solve it. So your average velocity is determined by change in position over change in time. Well, I basically gave you the answer while explaining your speed. Oops, I should not have done that. Maybe I should have left it up to yourselves. But your average velocity is just 0. 0 meters per second. And that is because your change in velocity. So average velocity is equal to change in position over change in time. Change in position is just 0 meters. You literally end up in the same exact spot. You end up maybe on your bed, doom scrolling, playing Adventure Capitalist like I was this morning. But you just end up with 0. So if your change in velocity over change in, not change in velocity, if your change in position is just 0 meters, we already calculated time, 2.208 approximately hours. Well, it doesn't matter. You just get 0 meters per second anyways. So your change of velocity is 0 meters per second if you didn't move at all. And technically, everyone's change of velocity is, average velocity throughout the day is just, well, 0, because you end up in your bed every single day. Maybe you move, toss and turn a little bit in your bed, but approximately it will be 0. Actually, I take back what I said about average velocity. Technically, homeless people don't really sleep in the same spot every day. That's an exception to what I just said. And in this problem, you have a different kind of approach. You have direction west and east now, so I didn't have to give you any path or anything like that. Last problem, you assumed one-dimensional movement, but in this problem, it's kind of guaranteed. So let's kind of write that down first. So you traveled. Let's see, you traveled 50 kilometers. 50. Okay, I need to find the straight line tool. You traveled 50 kilometers. 50 kilometers west. So this is west, and direction to the right. So we're moving this way. This is 50 kilometers. And you move back about 20 kilometers. So maybe this is about 2/5 of the way. Okay, I need to use the straight line tool. Straight line. There you go. And this is 20 kilometers east in this direction afterwards. And you're given your speeds, 30 kilometers per hour and 20 kilometers per hour. Let's find the average speed first. So average speed, remember, average speed is defined by distance over time. So how much distance did you travel? Well, distance is just equal to, well, you traveled 50 kilometers to the right, and let's associate right with the positive direction, typically associated with the positive direction, and this is negative, and you traveled 20 kilometers to the left. Well, since you're traveling average speed, you're only caring about distance, so distance is a path function, so you just add 50 kilometers plus 20 kilometers. And that's equal to 70 kilometers as your total distance traveled. And let's solve for the time now. So time will be solved by, well, again, you divide distance by speed. If you divide distance by speed, you get time. And if you do this, you get 5/3 hours, which is quite the long time. This is 1 hour and 40 minutes, technically. 1 hour and 40 minutes, technically. And if you divide distance, so 20 kilometers, distance divided by speed again, in the east, so traveling east now, you get, well, this is just 1 hour. So if you add these two together, 5 over 3 hours plus 1 hour, and this is equal to 8 over 3 hours. So we have our time now, we have our distance. So average speed is equal to, so this is equal to t. Let's box this in. So average speed is 70 kilometers over time, hours. And if you were to solve this in kilometers per hour, you would get 70 divided by 8 over 3. You would get 26.25 kilometers per hour as the average speed. Now, what if you were to solve for average velocity? Well, average velocity is different. You track change in motion. Change in position. Oh my god, I keep saying the wrong thing. Change in position. So your change in position is just 30 kilometers. And let me explain why. Well, if you traveled 50 kilometers west and 20 kilometers back east, you just end up at this point. And this point is just at 30 kilometers. Right? So if you divide, so velocity average is equal to change in position over change in time. And in this problem, I'm going to set it equal to this. So we have 30 kilometers as your change in position over change in time. We already saw for the change in time is 8 over 3 hours. So if you write all this down, you would get 11.25 kilometers per hour.